Hello everyone, my name is Tang. I'm from Xi'an Jiaotong University and Huawei Cloud Computing Technologies Company. I am very delighted to have this opportunity to report my research and to discuss the present state of fair memory subsystem resource allocation strategies on such an occasion. I would like to concentrate my discussion on the research and development of Themis. Themis is a fair memory subsystem resource sharing with differentiated QoS in public clouds. The purpose for this talk is to update you on the performance impact of memory subsystem resource location in cloud environment, especially in the scenarios that the multi-tenant with the heterogeneous workloads. I shall take only 25 minutes of your time, and I have divided my presentation into 5 parts. The first point discusses the background of my research, and the second covers the workloads characterization and analysis in public clouds. The third concerns about the details of our solution, Themis. Themis involved a long-term resource allocation and a short-term resource sharing design. Last but not least, there would be an experimental evaluation for our solution by comparing the state-of-art work, followed by the conclusion part. With reference to the background, it should be mentioned that the cloud computing has made a tremendous impact on the IT industry, while a large number of cloud vendors provide users with various types of resources as services. Cloud vendors often collocate the workloads from the different users in the same server to reduce the cost of these centers operating. However, as the soaring demand for the services of different workloads in clouds, the performance degradation of workload collocation is gradually worth of attention because of the resource competition among all workloads. For example, the CPU contention would result in a long scheduling latency for the workload, which share the same CPU cores, like the ECS2 and ECS3 workloads. If we look into the microarchitecture, we should find that there is also L1 and L2 cache interference between these two workloads because each of them will need a cache warm-up for the CPU's execution. Further, when the OS scheduler trigger run queue rebalance, every workload will have an all equal opportunity of cache warm-up, which will extremely harm the tail latency of user-facing workload. Although we can assign each workload a set of exclusive CPU cores to avoid the cache warm-up, like the ECS1 workload, we are still facing the resource competition of last level cache. As all the CPU cores are sharing the same last level cache in the same NUMA node. With the computation in the last level cache, the traffic from the data reading from the main memory will improve and affect the memory accessing latency eventually. If we could get the actual performance degradation feedback of all workloads when regulate the resource provision, it could help us to develop fine-grained resource allocation strategies. However, in public cloud environment, application-level metrics are not available to us. A cloud provider does not and should not have the visibility into the client's workloads running as the containers or virtual machines. In fact, many OPEC running workloads from the tenants can be classified as latency critical or best efforts categories by leveraging some statistical models for all the machine learning techniques. The latency critical workloads are usually performance sensitive, while the best efforts are usually performance insensitive. So we could give the LC workloads a higher performance guarantee than that of B workloads. Intel's resource directory technologies give us the ability to allocate the last level cache and the memory bandwidth. The RDT have 5 techniques, namely the CET, CMT, MBM, MBA, and CDT, while the CET and MBA responds for the allocation of last level cache and the memory bandwidth allocation. Both of them define a per software thread tag called the class of service. Class of service enable the running threads applications of the virtual machines to be mapped to a particular bandwidth settings in the underlying hardware. And class can be and this can be found in the left figure. And based on the class of service abstraction, we could give the hint to the RDT to allocate the specific resource of LLC and memory bandwidth sorting values for any target workload. For example, there are four class of services. In 1 to 4, we could give 4 exclusive cateways to the class 1 and 2, and 6 and 12 cateways to the class 3 and 4, and we can make the 6 cateways to be shared by the class 3 and 4. By leveraging the CMT and the MBM, we could monitor the actual resource consumption of all classes of service in the real-time manner. We investigated the temporal memory access patterns of both LC and VB workloads. We find that the workloads usually have a diversity of memory access patterns, and they change in tempo phases. For example, the left figure shows the memory bandwidth resource demand of the MongoDB under the diagonal workloads pattern. Obviously, it also demonstrates a predominant diagonal pattern during the 12 hours of light period. Besides, we could also find that the average memory bandwidth consumption is around 2 gigabits. In contrast, the B workloads prefer to consume extensive memory bandwidth to finish its job as soon as possible. The right figure illustrates the memory access pattern of 6 FMPEG collocation. It should be mentioned that due to the contention in the memory bandwidth, there's about the 52% of performance degradation for each of them. For the resource regulating respect, we found that the multi-netly regulating both the number of last level cache and the memory bandwidth limits could give us a better effectiveness to control the resource allocation. We first find out the performance baseline of the MenCacheD, Nginx, and the MongoDB individually, and then we evaluated the difference between their performance under the collocation with a stream workload. To quantify the impact by regulating a variety of combination of the cache waste and the number of the memory bandwidth sorting values for the stream workload. These three figures shows that as the stream gets more memory subsystem resources, all the LLC workloads shows a higher performance degradation. Based on this observation, we conclude that if we simultaneously regulate the last level cache waste and the memory bandwidth limits, can give a good controlling performance for the memory-intensive workload, such as the stream. We also find that the clustering virtual machines, according to their memory bandwidth demand, is a good solution to balance the system throughput and the fairness in a high-density public clouds. There are two main reasons. Firstly, the number of the clouds in physical host is limited, depending on the specification of the hardware, and is usually much less than the number of host virtual machines. So, assign each virtual machine to a separate class is not feasible. The virtual machines have to be grouped into the same class and share the resources allocated to the class. Secondly, if multiple virtual machines having the memory subsystem resource demand at a different order of the magnitude are assigned to the same class on the same NUMA node, their computation for memory subsystem resource cannot be regulated properly, as the memory bandwidth resource is heavily consumed by the virtual machines with higher demand, resulting in the unfairness to other workloads in the same class. This figure shows how the memory bandwidth and the latency varies when the MemCacheD is collocated with FMPEG and stream on the different class settings. We could find that if the FMPEG and the stream are assigned to the same class, we can guarantee the MemCacheD's performance. Well, we bring some the formal concepts and definitions to facilitate the discussion of memory subsystem resource memory management in Themis. The first one is the quota unit, where we configure the proportional relationship between the cache weights and the memory bandwidth threading values on the clause settings. The second one is the clause utilization, where the average memory subsystem resource utilization of assigned the quota units to a specific class. We also assigned the resource weight for all the workloads, namely as the virtual machine weight. For latency critical workloads, we assign them a high priority. For best effort workloads, we assign them a low priority. Based on this, class weight is a sum of the associated virtual machine's weight. And based on the class weight and utilization, we bring utilization well resource allocation strategies to assist the class reconfiguration. Before we regulate resource for the workloads in Themis, we should classify the workloads as LC or BE. Without the offline profiling nor the pre-knowledge about the underlying workload, we find that the egress network traffic usually changes with the ingress ones for the LC workloads. Almost all the requests are perceived and corresponding responses are returned within a short observation interval. But this is not longer true for the BE workloads, as the BE workloads usually show a batch pattern. Their results are returned after a long processing period, usually from tens of minutes or to the several hours. So we hypothesize that the LC workloads induce the relatively stable ratio of the ingress bytes and the egress bytes at the micro level. So we use the coefficient of variation of the ratio of ingress bytes and the egress bytes in the rounding phases to classify the workloads as LC or BE. After getting the results, we assign each workload a weight to reflect its sensitivity to the memory subsystem resource. We have two weighting rules. Firstly, the weights of all workloads in the LC group are greater than those in the B group. Secondly, the workloads in each group are weighted according to the reciprocal of resource requirements. Here we take a group view of Themis. Themis is designed as a two-linear management architecture. The upper linear focuses on how to group virtual machines with similar resource amounts into each class and configure the memory bandwidth sorting values and the number of LCVs allocated to each class. The bottom linear of Themis focuses on the resource sharing among multiple classes. Themis continuously monitors the memory bandwidth consumption and transparently enables the effective management of memory subsystem resource among all the virtual machines. In the upper linear, the Themis includes a long-term resource allocation. It adopts Euclidean k-means algorithm to periodically cluster guest virtual machines based on their similarity of recent memory bandwidth consumption. Each cluster is considered as a class in the RTT. And the CPU calls associated to the virtual machines in the cluster assigned to the class. How to estimate the best number of clusters is one of the major challenges for our solution. Considering the fact that our hardware platform is equipped with 8 classes of memory bandwidth allocation, we simply limit the k-means clustering method to group up to 8 clusters. In order to evaluate the cohesion and separation among all the clusters, we compute the silhouette coefficient. We also enable a safeguard mechanism for the Themis if the memory bandwidth consumption among the numerals exceeds 60%. We stop the long-term resource isolation and start to do the VM migration. Themis also included weighted time division multiplexing. for the memory subsystem resource sharing in the context of class weights. The Themis adopts two policies to allow tens of virtual machines to share a limited amount of memory subsystem resource, proactive and reactive. Proactive policy works for the improving the resource utilization among the multiple classes, and the reactive policy is used for the migrating the local hotspots among the neural nodes. This figure gives a brief description about how TTM works among the multiple classes. Suppose there are three classes, namely as the class 1, class 2, and class 3. They have different class weights, 6, 4, and 3, and each class has its own allocation of CPU cores. When it comes to the scenarios that the class 2 has a relatively lower class utilization, one of its allocated quota units will be shared among other classes in a WTDM fashion, considering the fact that the weight of class 1 is twice that of class 3, so the class 1 gets twice the net time slices for the use of this quota unit. And the class 3 start to use the shared quota in round 4, and the process will repeat until the quota units are reallocated among all the classes. Themis is evaluated in our cluster of inter-physical server. All the virtual machines are pinned to exclusive CPU cores, and the weight of all workloads are set as these figures. We set the 16 for the NGX, 16 also for the main cache, and the 1 for stream. These figures can be computed based on the workload weighting rules. To quantify the extent of performance degradation, we define the normalized progress (NPI) for the VMI. Based on this, the fairness is defined as this equation. WPI denotes the weighted progress of VMI, and the fairness is the minimum ratio of relative normalized weighted progress of any two workloads running on the same neural node. We evaluated the effectiveness of long-term class dynamic configuration in scenarios where all the LC virtual machines and the stream run under the constant workload levels. We initialized the FMPEG workloads at two different time points, the 30 and the 60 seconds, and we observed the clustering result until all the FMPEG workloads finish in the end. And according to this figure, the MongoDB, MinCache, and NGX workloads are assigned to one common cluster at the beginning, and the stream is assigned to a separate one. It is because the memory bandwidth consumption rate of individual LC workloads is at around 2.5 gigabits per second, while that of stream is at around 35 gigabits per second. It should be also mentioned that although both FMPEG-1 and FMPEG-2 workloads are not started at the beginning, their memory bandwidth consumption is almost zero from the virtual machine's view. So both of them are assigned to the cluster where all the LC workloads are. After FMPEG-1 and FMPEG-2 workloads are started, Themis divided these workloads into three clusters, and the clustering result is maintained until the FMPEG finish their execution. In the end, the clustering result fall back to two clusters again, as the stream and the LC workloads are still running. To evaluate the necessary and effectiveness of WTDM in Themis, we compare the WTDM-enabled Themis to the Themis without WTDM. This figure shows the memory bandwidth consumption among multiple workloads. The case for the with WTDM and without WTDM are independently enabled during these two periods, respectively. We we could find that with the case that with WTDM ensures that LC workloads use similar amount of memory bandwidth resource as in the case of without WTDM. It also enables the B workloads to utilize the more idle memory bandwidth resource to meet their the capacity demands while guaranteeing the long-term resource isolation of all the LC workloads. We compare Themis with other memory subsystem resource allocation strategies, where the no queues means that the execution of the LC and B workloads is not regulated by any queues control mechanism. This strategy serves as the baseline, and the MBA dynamic strategy is the dynamic algorithm similar to the technique described in the recent state of the art work. The MBA throttling value is changed as the running time according to the perceived memory subsystem resource contention. This table shows the performance degradation of all LC workloads under different control strategies. We can find that Themis effectively reduces the performance degradation of all LC workloads compared with no queues and MBA dynamic strategies. Themis also improves the fairness by up to about 105% and 72% compared to no queues and MBA dynamic strategies, respectively. And this can be explained that as the B workloads using disproportional large amount of memory subsystem resource in no-queue strategies. Although the MBA dynamic strategy improves the performance of LC workloads, it does not consider the priority and fairness of collocated workloads. Another reason is that the MBA dynamic strategies does not regulate the allocation of the cache weights for the last level cache. As a result, the performance improvements of LC workloads through the MBA dynamic strategy is inferior to that of Themis. Here we comes to the conclusions for this work. Firstly, the black box workload in public cloud calls for the new technologies for the allocating memory subsystem resource. Secondly, Themis adopts robust and online techniques for classifying workloads as B or LC and react to their resource demand in an online manner. Thirdly, Themis enable a priority-aware and fairness-aware memory subsystem resource management strategy that can guarantee the performance of high-priority workloads and maintain fairness across all the workloads. Last but not least, Themis is able to manage the memory subsystem resource for NUMA systems. That's all. Thank you for your listening.